My name is Igor. I'm going to be presenting this talk with a mouthful for a name, but basically what I want to talk about is how do you test the compilability of your code? That's basically what the talk is about. And before we jump into that, before we jump into all the nitty-gritty details, I want to talk a little bit about who we are. Like I work for Apex AI. I'm a senior software engineer, and basically what we do is we code in C++, incidentally 14. We're a bit stuck because we're in the automotive industry and we create safety critical applications that we have to deliver to our customers eventually. So in the video here, you see just one example of such a task where a car has to autonomously park in some parking space. And in these situations, the errors have quite high cost. So testing has to be quite rigorous, and it's simply a must to have a comprehensive testing strategy. With the modern C++, we use more and more compile time polymorphism and checks as opposed to runtime. And as far as I know, there is at this point no way to know if something is compilable, to check if it's compilable or not. It either compiles for you or it doesn't. So basically, the question of this talk is how does one test if something is compilable in a more or less rigorous way, right? So that's kind of the gist of what I'm going to be talking about, and I will start with a decently simple example. I mean, it's going to be a little bit too simple, but I think it shows what I want to talk about, and it fits on the slide. But everything else, everything about this example actually also transposes to a more complicated example in real life. So imagine that we are designing some form of a user-facing API. And in this situation, it's going to be something pretty simple. We want to get a half of something, and we implement it in the following way. Right. So this is a very simple function, and it might be a little bit too simple. So let's throw some templates in it, because we don't want just floats to be the numbers that we care about, but we want a little bit more than that. So we say it's a templated function, and we want to get half of any type t. But then we think, well, the way we implemented it, and let's forget for a second that we could have used multiplication instead of division. It won't work for anything that is not a floating point number, or actually it won't work for like integers and numbers like that. So we use SFINAE, and we disable this function for anything that is not a floating point number, right? So that should solve our problem that we're trying to solve, and that makes the function decently generic for our use case. Of course, what function would it be if it wouldn't have some test? So we write a rigorous testing suite, which is here implemented with these two functions. Of course, it's very, very minimalistic here. We could have done much more than that and could have used custom floating point types and whatnot and used the type test. But we will use here, for the sake of example, we will use a vanilla GoogleTest framework, which is also what we use, what we're used to using. And we test that a floating point number can be halved and a double number can be halved. Of course, there could be many more tests, but in terms of this talk, at this point, I'd say this is enough to showcase this, right? So we write this test, and everything for now is pretty standard. And then we think about it a little bit and go like, hey, what happens if somebody passes an int? Well, the only thing we can actually do is to write a comment, because I believe the tests are part of the documentation of a library. So somebody will read those, and we want them to not be confused. We want them to know what is not possible with this library as well as what is possible. So we write, well, this should not compile, right? And we put some integer in there just to show that get half of 23 integer should not compile, but it is a comment right now. So then we're happy with ourselves, and basically we throw it into the rest of the code base. You don't have to read this code; it's the same code right there. It just shows that we have a huge code base. Well, under the definition of huge. So we throw it into the code base, we pack it into the customer instance, and we deliver it to the customers. And the customers generally like us, So they are happy about the new delivery. So they start using the instance that we've just provided them with. And basically what they want is they want to use this new function that we added. So they ask like, hey, give me a half of 23 float, and they give and they get an answer 11.5, which is to the degree of my knowledge, a correct one. So everybody's happy and everything works as expected. And then sometimes, of course, they will try to do the wrong thing. So they will try to ask for 23 integer, for a half of 23 integer. And in this case, because we use the SFINAE, remember the enable if, it's not a floating point number. So they will get a compilation error instead, which is, I guess, it's like the best outcome here. So it indicates an issue early. And I believe in the modern C++, that's what we aim for, right? Now, basically, it's up to them. Do they want to raise it up to us and tell, hey, something is, we want it to be different, or if it just indicates that they're using the API wrongly. And again, this can be arbitrarily complex example. This is just an illustration of a pattern here, right? So everything is pretty good until this point. And then at some point, we have some of our engineers who just woke up and they feel groggy and they didn't have their coffee yet. So they look at this code and they go like, oh my God, this is too complex. Why so much complexity? We don't really use it with anything apart from floats. So I know what exactly what to do, and I will simplify this code. So they simplify this, right? So they rewrite the code, and now it just accepts any template. For example, they're happy with themselves. They're sure that nothing is broken because we only use it with float numbers in our code base. They go sip the coffee and feel a bit better about themselves, leaving the system to validate if their test is correct. So they commit it, they push it, it goes to the CI server. So we of course have a continuous integration and continuous test framework built in, and then we run all of our test suite. Everything, of course, passes because nothing has been actually changed. We actually do only use this function with floats because what else can we use it with? Because nothing else would compile, right? So for now, everything is all right. And so we automatically create a customer instance, and then we can actually roll out this customer instance to the customers. And I believe you now start to understand what's going to happen next, right? So our customers, again, make the same mistake as they did before. So they try to ask for a half of 23. Arguably, you can expect them to do it with the current setup of the function. But in this particular case, for this particular API, this is a mistake. So they try to ask for it, and the answer that they get is 11 float. And remember why? Because we actually just divide by 2, and we passed an integer, so we will divide by integer, and we get 11. And when we convert it to float, it becomes 11 float. Of course, there can be like warnings and whatnot to protect us from this. But if it's a header on the library, nothing forbids the customer to just disable the warnings and use whatever else. And again, it gets more complicated on more complicated examples. But I believe that the gist is pretty clear here. So they get the wrong answer, and then everything goes up in flames because now their critical system has gotten the wrong answer, and they've been debugging this for a month, and they couldn't find the error, only to find that it was us who cost them a month of their time, right? So we really don't want that. We would like to avoid that and to be able to catch something like this as early as possible, ideally on compilation stage. But how do we do that, right? So let's dive into this a little bit more and try to understand, what went wrong here, like why it happened the way it happened. Basically, the idea here is that we were relying on some code not being compiled, right? Not being able to compile, to be compiled. And then, of course, we missed the change when somebody made this code compilable. So when they made the get half of 23 integer compilable, we missed this part because there was no test for this. And how do you even write a test like that? And our test suite also didn't help us really. So basically, what I want to talk about here in this talk is how to make sure that we can enforce this particular comment. How do we write like something that would help us to get to the point where if it's broken or if it's actually not broken, it would tell us, right? So let's look at this at what we propose right here. So this is kind of the main 2 slides of this talk. If you want to just know what it is about, But then afterwards, we will dive into a bit more details into how this whole thing is implemented. So we start with the same file that you've already seen. It's pretty unspectacular. And basically what we propose is to add very little to this, like actually barely any lines of code. We want to add one more header, this static test.h, and we want to add a little bit more macros. I know we don't like macros, but we didn't find another way to do that. So basically now, if you read the code, you kind of instantly get what will happen. So you have the static test. It's called halving or whatever. We can name it the way we want. And it clearly says that this line of code, the get half of 23, should not compile, right? This is what we want to achieve. We want to replace that comment with this code that actually will show us something like this in case it actually does compile. So this is a bit of a like a lot of code on the slide, but basically the main part here is something like when we run our tests, it should tell us that, hey, this line, you intended it to be impossible to compile, but it did compile and it must fail to compile, right? So now the test has failed. And so we get a runtime check for this, right? So that's basically what we want. And of course, after we fix the bug, we want to have a clean, beautiful output of the GoogleTest framework, where we have this compile static test being returning an OK, right? So now that we know what we're talking about, let's also talk about how this all can be done, right? And let's start with the basics. So this is a pretty standard testing pipeline, nothing new here. We start with some text file which holds some code. We give some flags through some build system, be it CMake, Bazel, Meson, or whatever else build system that you want to use. We pass this whole thing into the compiler. The compiler does its work and spews out a binary, right? This is a test binary that uses GoogleTest internally for us. I guess it's also possible with a different testing library, but we use GoogleTest for now. And then GoogleTest basically says yay or nay. Did it pass the test or did it not pass the test? And if it didn't, then it's our job to fix it. Right. So what we propose here is to add a little bit more steps to this whole pipeline, basically these. And there's a lot of lines going on in this slide. So let me just a little bit slow down and go over all the particulars here. So basically what we will be talking about and what we propose, what is part of the library that we propose to have is just this colored part of this slide. And basically it consists of 3 distinct actions that we have to do. Basically, we have to generate the compilation tests. In this particular case, they will be called like test compile 1 and test compile 2. Then we feed the generated tests to the compiler with the correct flags. And with the correct flags is a big thing here. We will talk about this later. And then the compiler does its work and spews out the result, and we have to interpret those results, right? So this is basically all the 3 things that we have done, and there is really nothing more than that we have to do. Now the question is, of course, we need to understand how exactly that can be done. So let's look even more into details here. And basically what we do is we build upon the GoogleTest library, as you've already understood, by using a custom fixture, which we will look at on 1 or 2 slides down the line. And we introduce the following macros. We have the static test macro that basically wraps our test. And we have the should not compile and should not compile with message macros that basically are able to test if something is compilable or not. And these macros, they do nothing else than hide custom calls to custom scripts that do all the dirty work behind the curtains, right? They basically, these scripts, they generate the files, they feed them to compiler, they get the flags, and they interpret the compilation results. And we are at CppCon, so let's look at some C++ code. It's nothing really spectacular, and these are, of course, macros, but please bear with me here. So this is all the code that defines, in reality, those macros. So it's not really that complicated on the C++ side. And basically, here we have a couple of things that I want to walk over. So the static test macro does nothing else as it defines or declares a child of the static test, which is our custom Google test fixture. We will look at it on the next slide, or in 2 slides or so. And basically, this static fixture, this static test custom fixture does all the work internally. So what we do here is we create a new class that is inheriting from that static test fixture, and all the work is happening in the constructor itself, right? And then we actually write a test in the Google test framework that basically will hold all the code that we write afterwards. So for whatever is not wrapped in the should not compile macros should still be compilable and runnable. So we want it to be a real C++ code. And then if we look at the should not compile and should not compile with message macros, they do nothing. They basically are empty macros, and they just serve as tags for whatever external tool that we use to generate our code, right? So they do nothing on C++ side, but whatever tool we use, we'll look at them and we'll know how to generate code from that. We will get to the details of this a bit later. Now let's look at this at the static test custom fixture, right? Again, this is nearly all the code that you need for this. It's a little bit stripped down because of the slides, and some details are left out, but overall, this is exactly what works, what actually does the work, right? So we have a class, which is just a Google test fixture, and it accepts a name and a file, or a file name to it. And what it does, it constructs a command string that calls some external script. In this particular situation, I just called it command, but in reality, it is a Python script in the background. Then it runs it with, in this particular case, with std system. But basically, if you have your own fancy runner, you can also do that. And then the final step, last but not least, we have to check if the exit status is actually what we expect. So we expect a 0 for success. So our script must succeed in failing to compile everything, if that makes any sense. And if it doesn't fail to compile something and returns a non-zero error code, we actually want to tell the user that it did not happen. So basically, at this point, we just insert another error into the Google test, and we do it this way because it's in the constructor, so there is no return value, and that was just the easiest way to do that. But generally, there is no rocket science here. Right. Now, with all of this out of the way, let's talk a little bit more about that external script. And external script is basically just some script that we could use from within, right? So basically, it parses the original test file as text. It generates these new test files from each of the static tests in the original test file. It gets the proper flags for the original test file and reuses them to pass those to the compiler. Then it, of course, feeds the generated tests to the compiler, interprets the results, and returns an error code to the fixture. Basically, the script can be written in any language as long as it can be called from within our static test fixture. Now, let's kind of do a small step aside and try to understand what happens when we have to generate these files. Like, how do we generate a concrete set of files that we need to test for compilability from a given test? And we've seen this test before. It's a little bit modified because we also added the should not compile with message here, where we pass a string instead, and we add a message that it has to take care of. So basically, the first step that it has to do, it has to copy everything that is not within a static test to all the generated files. And at this point, we just copy over the headers, but anything else that would fall there, like namespaces or whatever else, would also get just straight copied to the new generated files. The next step is that every static test is generating like a main function that we want to use within our generated file, and it could be anything. But we decided that the main function is like, I mean, we have to have some form of a main function to run it or to build it properly. And then, but basically, the whole idea here is that it just has to be. We have to be able to build it, and that's basically it. And then each of the should not compile style macros, they generate a separate file. So this is a little bit like, I'm still on the fence about this myself. We could have just put them into one file, but then it's a bit harder to find out what exactly failed and then return that back to the user. So we have to actually split them out into the separate files. And with that, basically all the kind of the dirty deeds are done. We have the two files, we feed them into the compiler and then interpret the results. So there is really not that much to talk about here. The one more thing that we do need to talk about is how do we get the proper compilation flags, because it's not that trivial. At least we didn't really find a trivial way to get that. Basically, we need to feed exactly the same compilation flags as we did to the original test, right? Because the original test only compiles or doesn't compile because of the flags that were passed. So if we, for example, remove the minus W error flag or something, it drastically changes the output. And what we want is we want to pass the same flags. I believe there are two broad ways to do that. And this external script basically takes care of that too. We either compile our tests with the -f record GCC switches. We mostly work on Linux, and I believe that both GCC and Clang, they both support this type of a flag, and they can record then all of the compilation parameters into the strings part of the actual binary. So then we will have to take that binary, read the strings from it, get the flags, use those flags when passing the things into the compiler. Or if that is not possible, if you cannot just add the frecord GCC switches flag to your test targets, then we can generate a compilation database and then parse this compilation database. I do that a lot in my plugin where I for the C++ auto-completion for Sublime Text, but and that's basically where the idea came from. But the core idea is that CMake or Bazel, they both can generate a compilation database, and then we can just parse that database to get the proper flags. And the last thing that we have to talk about here is basically what does it mean to fail or succeed in this static test? And it's kind of relatively simple, right? So if a should not compile, like for each should not compile, if the compilation of the file that it generated fails, then the static test if the compilation is successful, then the static test fails, and we get this message that we've discussed before. And if the compilation fails, then it's kind of vice versa. We print the static test success message, and everybody is happy. And with the should not compile with message, it's a little bit more complicated. Basically, if the compilation is successful, it's still the same. The compilation should not succeed. So that's pretty. It's exactly the same, right? So we would still fail the static test. But if the compilation fails, then we actually have to check if the message is it matches some specified pattern, or actually if we find the specified pattern within the message. And if we do, then the static test actually succeeds. And we basically just added the should not compile with message for the use when we have a static assert or something with a nice message to it. And of course, if we don't find this pattern, then the static test actually fails. So this brings me to the end. Basically, with this, we would be able to test the compilability of the code. At least I don't see another way around using the compiler in the loop. which actually comes with the downsides that depending on your code base, it might take a while to compile something. So a lot more work has to go into the tooling to make sure that that this all happens quickly and that we can reuse the pre-compiled parts. We do the integration with the GoogleTest library. We could, of course, integrate with a different testing library. I believe that the machinery is kind of still available for doing what we want to do here, but we are used to GoogleTest library, and that's why we picked that. And basically what happens is we generate the custom tests that compile the generated code. If that compilation succeeds, we fail, and vice versa. The downside here is that most of the functionality lives in an external script called by a fixture, but the plus side, you can write it in whatever language you want, and it can basically do whatever you want it to do. And this allows us to catch bugs that were basically impossible, at least to the degree of my knowledge, to catch before. So the final product is in the end more safe to use. So now the bad news is that we don't have a ready-to-use implementation that everybody can poke around. And hopefully the proof of concept implementation is going to be incoming sometime soon. But that's basically everything that I got. And I think we still have about 4 minutes or so. I'm happy to answer any questions. And I guess I see a couple in the Q&A. Okay, should I just go over like from the top? I don't see any. Yep. Okay, I'll go from the top. So the first one is, what's your process to make sure everything is fully tested? Code coverage is usually not enough. Well, I mean, code coverage is enough, but not line coverage, right? So I'd say this is a bit that's not really related to this particular talk, unless I'm missing something. And I'd say that, I mean, we can of course talk offline about this, but I don't think that this is related here. So long story short, code coverage actually is enough, but you have to cover all the branches, and that is hard to do. So we do that, but it's a different talk. Okay, so the next question is, why gtest and not catch2? I find catch2 much easier to use in most cases. Yeah, could be. We use gtest internally. We have a lot of tooling based on gtest, so that's why we used it. But again, I think catch2 is also a pretty good possibility there. I think we still have 2 minutes. All right. Maybe I should. Okay, I will go in order. Is external script necessary? I thought this can be achieved with SFINAE generated by macro, something like, okay, what decouple type expression. So the thing is that whenever you use SFINAE, it won't compile in certain cases, right? Then when do you know, like, how do you test that it doesn't compile or something? So you have to, unless I'm misunderstanding the question, you do have to run the code eventually and compile the stuff that should otherwise not compile. How do you otherwise test that it is compilable? If I misunderstood this, I'm again absolutely happy to talk about this offline. Right. Then the next question for the last minute is, how do you deal with the test binaries that get moved out of the build tree before executing? Like a test binary that first gets deployed to target hardware and then executes there. What will happen to a static test in that case? Let me think. Okay, then that would need to have an extension for this library in order to be able to still get the pass to them. Like I believe if they are moved out of your system, then it's going to be much harder. But I believe that in most cases, the test binaries would still live on the system. And also, it doesn't have to be done for like all the different flavors, right? You can have this built for like the x86, but then not build it for like something like an ARM or something like that has to run on a different platform. So I'd say that if you want a general solution, then it has to be moved out. But other than that, it has to be extended. But other than that, I think you can always build your build system in the way that it actually has the test files handy and only test these particular types of tests there. I hope that answers the question. And I think we ran out of time right now. But I will look at all the other questions, and we'll try to answer them in the chat or in the GatherTown if I manage to log in. Thanks a lot. I hope to have fruitful chats later. Thank you.